Okay, so this is the first video on about the mole, basically in chapter 3. It's kind of, this is the chapter that I call the mole chapter. It's all about molarity and the mole. So the text is really good, Cindy, about describing the motivation for having something called the mole. It's basically a number, and it's arbitrary, but it's if you think about molecules again, all the chemistry happens at the molecular level. And the actual weight or amount of substance involved at the molecular level is incredibly small, right? So if we were going to try to answer questions like when you burn some amount of methane, how much carbon dioxide is produced? If we tried to use the units of mass at the molecular level, it would be really tiny numbers. And in our observations, we want bigger numbers. So essentially, a number of molecules was invented, or actually the text says a number of entities was invented. It's quite arbitrary, but they basically said if you had 12 grams, exactly 12 grams of carbon-12, how many carbon-12 atoms do you have? So this was just kind of it was an arbitrary number. They picked 12 grams, kind of, I want to say almost like randomly. It wasn't randomly, but they chose 12 grams of carbon-12, and they actually used the measurements for the weight, for the mass of a carbon atom to determine how many atoms there are. And it turns out it's this number. Where's my pen? I think I'd have it ready, but I don't. Here it is. It turns out when you figure that out, it is a number called, it's number 6.022 times 10 to the 23rd. That's a magic number in science, and after a while you will memorize this number because it's used in many calculations. It's also known as Avogadro's number, after presumably someone named Avogadro, but I don't even know the story there. So this is essentially a mole. And again, a mole really means that's a reference to a quantity, a number. It's almost like a dozen. So a mole is like a very big dozen. But the word dozen and mole are similar. It just means a certain exact number of something. Okay. So this is used, and it's very handy, and you'll see it because we're going to do a lot of example problems. But you'll see where using mole in chemistry calculations is very useful. Okay. So I'm going to actually drop back for a second and draw back our methane reaction. Remember the methane. I'll draw the chemical reaction first. Remember, we actually did this in chapter 2. We did a reaction which was essentially burning methane. It was CH4 plus 2 oxygens yielded 1 CO2 and 2 waters. And again, I'm just going to always draw what these look like chemically, because that's kind of an important habit to get into. And 2 waters. Okay, make sure you can see all that. Yeah, you can. So this is essentially the burning methane reaction that we talked about when I introduced you to chapter 2. There's 2 things I want to point out here, and there's one that I'm probably going to save for another video. And this is kind of a follow-on to our conversation yesterday. Remember when I was talking about oxidation number? We were talking about the polyatomic anions with chlorine and oxygen. And we had all kinds of drawings where you actually made the discovery that chlorine in a +5 state had kind of 5 bonds to this oxygens, but chlorine in a +7 state had 7, and all that stuff. And I started to introduce you to oxidation number, oxidation state. I wanted to quickly just point out something here, and I'm going to follow back soon. Is remember in all of our discussions when we were talking about chlorine, I always said oxygen is always in a -2 state. Well, if that were the case, then I want you to ask yourself the question: if oxygen is always in a -2 state, how do you explain that an oxygen model that I drew as O-O, how do you explain that being having no charge? Very good question, because you'd expect O-O to have a 4- charge if if the oxygen atoms in this molecule, this oxygen molecule, were actually -2. But in fact, it's uncharged. The oxygen doesn't have a charge; it's neutral. So that's very important, and I want to follow back up on that. But I want to introduce you to the fact that this reaction here is actually one of those oxidation state reactions. So okay, so that's for future. The other thing I want to actually point out is that it ought to be reasonable when you actually look at this reaction to say, gee, if I burned so much methane, let's say, I don't know, some amount of methane, 36 grams of methane, or something like this, 32 grams of methane, how much carbon dioxide am I going to produce? And again, this is relevant in the whole climate discussion right now because of the fact that carbon dioxide being produced is of some concern, at least to some people. And this is a reasonable question. It's like if you actually say, gee, the climate is sensitive to the amount of CO2, then it would be good to know for various things that you burn, like in this case methane, how much CO2 is produced. Well, the mole concept allows us to actually produce, determine the answer to questions like that. But again, if you looked at it at a molecular level, you don't really have the answer. What you have is, well, if you burn 1 molecule of methane, you'll make 1 molecule of carbon dioxide. But that's not the question. The question is, if I burnt some mass of methane, how much mass or weight? Mass and weight are similar. How much CO2 from a mass perspective is produced? And again, this equation shows molecule to molecule, but it does not show mass to mass. And the whole discussion of chapter 3 is about making calculations like that. Okay. So I am going to erase our little picture here, and I am going to draw another reaction, different reaction. I hope I don't have too much time here. Yeah, I'll squeeze it in. And if this goes long, and maybe I'll chop it and re-pick up on another video. Okay, so the one I want to actually talk about here is the reaction ethanol, also known as alcohol, the alcohol that we drink in beer, wine, etc. Burning, basically mixing with oxygen. What do you think is formed? Well, I can tell you that ethanol is an organic compound. And pretty much all organic compounds, when you burn them, if you're able to burn them, sometimes you need to incinerate them or get them to high temperature before you can burn them. But in the case of ethanol, if you had pure ethanol and you lit it on fire, it would burn. It burns like a blue flame. It burns very, very hot. Now, burning ethanol mixed with a lot of water, like in whiskey, it doesn't burn. But if you had really, really strong alcohol, it does burn. And you've probably seen this in lighting desserts on fire. They pour some really high alcohol, like high alcohol content rum on in your dessert, and then they light it on fire, and it does indeed light. So when ethanol burns, just like any other organic, when it burns, it produces carbon dioxide and water, some amount here. So I'm going to actually now draw this chemically. So ethanol, let me draw what it looks like. Ethanol is using eth, which is the Latin, it means 2 carbons, and one of the carbons is surrounded by H's, and the other carbon is surrounded mostly by H's, but it has room for one thing that's not an H. By the way, if this were an H here, this compound is ethane, very much like methane, but ethane because it has 2 C's. But ethanol, it doesn't have an H at the end, it has an O H at the end. So it's an oxygen and a hydrogen. This is the ethanol molecule. Okay. So when ethanol burns with oxygen, it's going to burn with some number of oxygens like we had, and it's going to produce some number of CO2s and water. Now, if you remember in the original methane burning example, there was a discussion of, gee, well, how many of what and all that. And I'm going to start that discussion right here. Actually, no, I'm not. I'm going to end this thing, and I'm going to start this on the next video. Okay? So I'm going to pause this here.